Dear colleagues, today we consider vehicle routing problem. This is the problem to deliver certain goods from the central warehouse to the customers. And the method which guarantees optimal solution to vehicle routing problem is unknown. And for this reason, we will consider heuristic algorithms and to solve such a problem, very well known heuristic solutions such as genetic algorithm or greedy algorithms or more powerful meta-heuristic algorithms are used. Heuristic solution means that such a solution does not guarantee optimality. So it is non-zero probability to find an optimal solution with heuristic solution, but nevertheless, heuristic solution does not guarantee optimality to this problem. But from another point of view, heuristic solution is reasonable and in general proposes rather good solution. Today we consider very well-known heuristic solution to vehicle routing problem, which is known as Clark and Wright saving algorithm. Problem statement and introduction to Clark and Wright saving algorithm could be found, and I propose you a paper which includes all the information about the problem statement and also proposes the heuristic solution Clark and Wright saving algorithm to vehicle routing problem. And also it proposes two variants of Clark and Wright saving algorithm. The first one is known as sequential algorithm and the second one is parallel algorithm. We will consider today only sequential algorithm, and also you may read about parallel algorithm. You are welcome. Visualization of vehicle routing problem could be the following. We assume that there is a central warehouse or a depot, and we assume that we consider one product problem and we consider only one depot. And also we assume that there is unlimited stock at the depot, and also we assume that there is unlimited fleet of vehicles which are at the depot, and assume that vehicles deliver our goods from the depot to the customers. And also assume that all the capacities of the vehicles are the same, and we denote the capacity with the parameter C. C, it is for instance 5 tons, it is the capacity of the first vehicle. The same capacity C or 5 tons, it is the capacity of the second vehicle, and so on, and the same capacity for any vehicle. Assume that there are n customers at this map or at this region, and this is the locations of the customers on the map, and we assume that for each customer a certain demand is given. For instance, it is the first customer and the demand for the first customer is d small 1. It is the second customer and demand is d small 2, and so on. And this is the customer number n, and demand for this customer is d small n. In general case, demand of the customer I we will denote with di. The next assumption is that capacity of the vehicle exceeds or equivalent to the demand of each customer d small I. We assume that capacity of our vehicles C is more or equal to demand of each customer. Also, the problem is we should deliver our goods from the central warehouse to all the customers, and each customer should be visited only once. Demand of all the customers should be satisfied, and it is possible because the capacity of vehicle is enough to meet these restrictions. Also, we are given the information about the distance between any two customers on the map and also between any customer and the depot. And the problem is to satisfy all the demand with the minimum transportation cost. Let us collect all the assumptions. So the first one, we consider one product. So we consider assumptions And the first one is that we consider one product problem. Also, we consider one depot or central warehouse. The next assumption is we consider unlimited stock at the depot. Assumption number 4, that we consider unlimited fleet. So amount of vehicles is unlimited. We consider unlimited fleet. The assumption number 5, we consider the same capacity for all the vehicles. The same capacity for all vehicles. And we assume that this capacity is C small. Assumption number 6, we consider N customers. The next assumption is demand of a customer I is DI. So demand of a customer with the number I. So demand we denote with D small I. And the next assumption, assumption number 8, is that demand of each customer is less or equal than C. And once again, C, it is the capacity of the vehicle. And when I runs from unit till N. So, and 1, it is the number of the first customer, and N, it is the number of the customer number N. And the next assumption, each customer should be visited only once. Should be visited only once. And also the next assumption, assumption number 10, is that distances between all customers and depot are known. All the distances in this problem are known. So we may get this information from the map, and of course if we consider a practical problem, so we consider a lot of customers, so N could be rather big. And of course manual calculations for these distances takes a lot of time, and we should consider some program realization of such a request to a system, to information system or geosystem, which allows us to get all these distances automatically. And the problem statement is the following. So the goal of the vehicle routing problem is to satisfy all demand with minimal transportation cost. With minimal transportation cost. So it is the vehicle routing problem. So vehicle routing problem. So it is the abbreviation vehicle VRP, and this is the visualization of this problem. So and this is the assumptions of the problem. So the feasible solution is rather simple. So we may take the first vehicle and we may assign this first vehicle to the first customer, and this vehicle takes D1 units from our depot and delivers this to the first customer. This demand of the first customer now is satisfied, and the empty vehicle goes back. So also we may consider the second vehicle, which takes D small 2 demand of the second customer from the depot and delivers it to the second customer and goes back, and so on for all the other customers. So this solution is feasible, and because demand of each customer is less or equal than capacity, we may satisfy all the demand of all the customers, and also amount of customers is n, and there are unlimited amount of vehicles at the depot, and for this reason we may every time assign a certain vehicle to each customer, and so this solution is feasible. So it could be realized, but we may see that this solution is rather expensive. We waste a lot of time to deliver goods from the central warehouse to each customer separately, and we may consider alternative, for instance, when the first vehicle goes to the first customer, and if it is possible to load into this track the demand of the second customer also. So we may consider alternative route, for instance, when we start at the central warehouse, we go to the first customer, after that we satisfy demand of the first customer, and we go to the second customer, we unload our vehicle, and we satisfy the demand of the second customer and go back. And if it is possible also so to load the demand of the first, second and third customer into the track, so we may save more distance or more time. So, and we start from the first point, the central warehouse, go to the customer number 1, to the customer 2, to the customer 3, we go back, and we save maybe more rather than when we go to all the customers separately. And this is the idea of the Clark and Wright saving algorithm, in which we compare the distance in the case when we go from the central warehouse to the first customer, go back, go to the second customer, go back, and we consider the second case when we go from the central warehouse to the first customer, then we go to the second customer, we go back, and we calculate the difference between the distance from the first and the second case, and we call this difference savings. Let's consider this idea in more details. We consider the first case, case A, so in which we start at the central warehouse, we go to the first customer, and the distance, assume that distance is COI. So now C denotes distance when we consider C with indexes, so it means that we consider distance. If we consider C without index, so it means we consider capacity. And let's continue. Assume that the distance from the customer number I to the central warehouse is CIO. We consider the symmetric case in which COI and CIO are the same. So the distance from 0 point to the customer I and the back way, so the distance from the customer number I to the central depot, so are the same, and these distances are the same. So, and also we consider the distance from the central warehouse to the customer J, and it is COJ, and also the distance between customer J and the central warehouse, so it is CJO. And now once again we assume that COJ equals CJO, so it is CJO, and it is the first case. And the alternative case, when we start at the central warehouse and go to the first customer, so and the distance is COI, and we consider the distance between customer I and customer J, and distance is CIJ, and the distance between customer J and O now is CJO. And if we consider the first case, the distance we may calculate as follows. So distance for the first case, case A, so we calculate as COI plus CIO plus the distance COJ and distance CJO. So, and I remind you that this distance and this distance are the same, and also this distance and this distance are also the same. For the second case, we consider distance for the case B, and we summarize COI plus CIJ and plus CJO. And we consider the difference between distance DA and the distance for the case B. And it is COI plus CIO plus COJ plus CJO. It is the distance DA for the first case minus the distance for the second case. So it is COI minus CIJ and minus CJO. And now we see that some distances could be eliminated. So for instance, COI, and here we see minus COI. And also there is the distance CJO, and it is minus CJO. And as a result, we get CIO plus COJ, or we may write CJO, because this distance COJ and CJO are the same according to our assumptions, minus CIJ. And this expression we will call savings for the pair of the customers IJ. So let us rewrite this expression. So it is CIO plus CJO minus CIJ. So, and it is savings for the pair of the customers IJ. IJ, they are customers, so, and there is no depot for the savings parameter. The same calculations are also represented in the paper. So, and it is the distance for the case A, it is the distance for the case B, and this is the calculations for savings. The idea of Clark and Wright saving algorithm is the following. So we consider savings for all the pairs of the customers in this problem. And after that, we consider the maximum savings in this case. So maximum saving when we consider the route B instead of the route A. So maximum savings mean that when we consider these two customers I and J in the same route, we save significantly. And it seems that it is the first priority to join these two customers I and J with the maximum savings into the single route. If it is possible, of course, from the capacity of the vehicle point of view and demand of these customers. So the idea is the following: we calculate the savings for all the pairs, and after that we rank all the pairs of customers according to savings parameter by descending mode. And after that, we start from the top of this ranked list of the pairs, and we consider, is it possible to join customers on the top of this list into the single route from the capacity of the vehicle point of view? And if it is possible, so we do this, we join these two customers into the single route, and after that we continue with the same savings, and we go down through the rank list of the pairs of the customers. Let's consider an example from this paper, and in this paper we consider a problem with 5 customers, and there is the first customer, the second one, and so on. And also the point 0, it is the depot. And the first point is a customer. And also on each row we also consider customers. And if we consider distances between any 2 points, so obviously the distance from depot to the depot does not make sense, so this distance is 0 obviously, and we do not consider such a route here. Also, distance between the depot and the first customer in this case is 28 kilometers, and so on. And for instance, we see the empty cell here. It is the distance between the first customer and the depot. When we start at the point where is the first customer and we go to the depot, so there is no information because we consider symmetric case, and if the distance between the depot and the first customer is 28, so it means the distance between the first customer and depot, the back way, so it is the same 28 kilometers. Also, we assumed that capacity of the vehicle is 100 units, so it is our C small. And the first table, so it is about Cij. So for instance, 28, it is C from the depot, so the first index is 0 to the first customer. So 28 is C small O1. So 100 units, it is C capacity. And also we are given the following information about demand. So the first customer's demand is 37 units, it is D small 1. And demand of the second customer is 35 units, it is D small 2. It is D small 3, D small 4, and D5. Let's consider the savings. According to our formula, savings Sij could be found as follows. So it is C small distance between customer I and the depot plus Cjo minus Cij. So this is the way how to calculate savings. So according to our symmetric case, once again let us rewrite Cij in more convenient form. So Cio, it is the same as Coi, we consider symmetric case, plus Cjo, so we may consider Coj, once again we consider symmetric case, minus Cij. And let us calculate S saving Ij for the case when Ij, it is the pair of the customers, the first and the second. So it is the first and the second customer. So we consider S1, 2, and in this case I equals 1 and J equals 2. And for this case we have the following. So it will be CO and I, it is the next index, and I now equals unit CO1 plus CO and J now equals 2 minus Cij minus Cij, I is 1, J is 2. Now let's consider the table with the distances. CO1 is 28 kilometers. 28 kilometers. CO2 distance between warehouse and the second customer, so it is 31. And minus C12, so C12, C1 and 2, it is 21. And we see that the savings for this case could be found as following. So it is 38 kilometers. And let's consider, for instance, savings when we join customer 2 and customer 3 into the single route. So in this case, I is 2 and J is 3. and it will be COI, and I is 2, plus COJ, J is 3, minus C2, 3. And for this case, CO2 is 31 kilometer, plus COJ, and J now is 3, so let it be 3 here. So CO3, it is 20, plus 20, and minus C23, so 2 and 3, it is 38. And if we calculate this, we will get 13. So savings 1, 2 is 38. Savings when we join customers 2 and 3 into the single route instead of visiting these customers separately, so the savings is 13. Now assume that we have found all the savings for all the pairs, and let's collect all this information into the table. Now, so before we consider the following table, so I would like to remind that saving 1, 2 is 38, and savings 2, 3 is 13. Let's consider the following table. So it is page number 5 of the paper, and in this table the savings as capital IJ are represented. So there is no warehouse here, only the savings for all the pairs of the customers. And we see that as capital for the first customer I equals 1, and the second customer number, so J equals 2, so S capital 1, 2 equals 38. And we have found the same information before, so S savings for the first and the second customer is 38, and savings for the second and third customer is 13. And here indeed we see this is the saving S, 2 and 3, and as we see, all the other savings are also represented in this table. Now let us find the maximum saving in this case, and as we can see, the maximum saving here is 42, and it means the pair, when we consider the first customer and the 5 customer, so if we join them into the single route, so the savings will be maximum, and it will be 42 kilometers. And as a result, the maximum saving we found for the pair 1, 5, and we consider the ranked list in which on the top there is a pair of customers with the maximum savings, so customer 1 and customer 5. So when we join them into the single route, so we get the maximum savings. The next maximum savings after 42, it is in this table, so it is 38, and it is the savings for the pair of the customers 1, 2. And for this reason we consider the second pair on the rank list 1, 2. And the same fashion we consider all the other pairs, and we see that on the bottom there is the pair of the customers 2 and 3. So, and it is the minimum possible savings in this table. Now, when we found the ranked list of the customers according to savings, we consider the sequential saving algorithm. To realize sequential saving algorithm, we consider the following table. I propose to consider the table where the first column is a pair, a current pair which we take from the ranked list. The next column in the table is a route to check. So this is the column in which we will consider the current route which we should check for feasibility. The next column is demand for the route to check, and the next is the question, is this route feasible? So to answer this question, if we answer this question, we check the feasibility of the current route. And so when we have checked the feasibility, so we consider the current route. And we begin with the pair which is on the top of the ranked list, and on the top we consider the pair of the first and the fifth customer. So the pair is 1, 5. And what is the route to check? So we assume that we every time start at the depot according to our assumptions, and we go to the first customer number 1, and also after that we go to the customer number 5, and also we go to the depot. And it is our assumption, and I would like to add this assumption into the list. It is the assumption 11. So we consider closed routes. So each route starts and ends at the depot. It means that we consider closed routes. Let us check the demand of this route. So demand of the first customer according to our problem statement is 37, and demand of the customer number 5 is 32. So the total demand for this route will be 37 plus 32. It is 69 units. And according to our assumptions and problem statement, so the vehicle capacity is 100 units, and it means that this route is feasible. We answer yes, the route is feasible. And the current route is the route to check, because this route is feasible. So now we consider the route which starts at the depot, goes to the first customer, then goes to the customer number 5, and goes back. The next pair in the ranked list is the pair 1, 2. So the next maximum saving we have found for the pair 1, 2, and the next pair we consider is 1, 2. As we can see, according to our current route, from the depot we go to the first customer, then go to the customer 5, and after that we go back. We see that there is a common node, which is customer number 1, common node in our current route and our current pair. And it means that we may physically join this pair to our current route, because there is one common point. And so our route to check is the following. So we start at the depot. Next, we go to the customer number 2. Then we go to the customer number 1. And here we join our current pair and our current route with this common node 1. So, and after that, after the first customer, we go to the customer number 5. And after that, we go back. Demand of the second customer is 35 units. And let us check the feasibility. 35 units plus the demand of the first and the fifth customer, which is already found, is 69. So for customers 2, 1, 5, the total demand is 104, and capacity is 100 units. And as we see, demand of the customers 215 exceeds the capacity of the vehicle, and it means that it is impossible to join these 3 customers in the same route. So it means that this route is unfeasible, and our current route is 0150, which is the same that on the previous step. The next pair on the ranked list is 2, 4. So let us consider this pair 2 and 4. And if we consider our current route 0150, there is no common points between our current route and pair which we consider. So we cannot join the current pair with our current route. So it means that it is impossible to add this pair into the current route. So, and for this reason we do not check feasibility, and our current route is still 0150. O. So the next step in the ranked list after 2, 4, so it is the root 4, 5. And this is the pair which we consider. And if we see that there is a common point in our pair and in our current root, and it means that we may join, we may add this pair into the current root and join them by this common node. And the rope to check is 0, 1, 5, and 5 it is the common point, and after 5 it is the customer 4. So and after that we go back, and let us check the demand once again. So demand of the customers 1 and 5 is 69 units, plus demand of the customer 4 is 25 units according to our problem statement. And as we see, it is 94 units, and the capacity of the truck is 100 units. It means that this route is feasible. So and our current route is 01540. And also we may continue with all the other pairs in this list, and we may check the feasibility if it is possible to add the new pair into this route or not. So but obviously, so empty space in our track is 100, the maximum capacity of the track, minus 94. So it remains the space only for 6 units. And according to our problem statements, we see that there is no demand of the customers which equals 6 or less units. So it means that all the other pairs, it is impossible to add, or demand will exceed their capacity of the vehicle. And it means that we should stop here, and the first route we found is the following. It is the first solution, and the demand is 94. So let's consider our ranked list, and we should exclude from the ranked list the pairs which already includes the customers in the first route. So it is the route 1 which we found, and now we should exclude all the pairs from the ranked list which include our customers 1, 4 and 5, because according to our assumptions, every customer should be visited only once. So the first pair we should exclude, because our route number 1 is 0154. And go back to the depot, and the first and the fifth customer are already satisfied, so we exclude this pair from the list. And the pair 1, 2 includes the customer 1, so obviously 2 is not in the first route, but it does not matter. The first customer is in the route, so that's why we cross out this pair. So the next pair 2, 4, customer number 4 is already satisfied. The next pair 4 and 5, so we visited both these customers. 2, 5, the customer 5 we already visit, and 1, 4, once again both these guys we already visited. And 3, 5, so 3 is unsatisfied, but customer number 5 is already in the route 1, so cross out this pair. 1, 3, customer 1 is already satisfied. 3, 4, customer 4 is already visited. So 2, 3, so there is no customers 2 and 3 in the first route. So it means that from the our rank list, so after the construction of the first route, so it remains the list of the pairs which includes only one pair. So originally it was the first list 1, and after the construction of the route 1, so we consider list 2 of our pairs, but list 2 includes only one pair. So it means that we continue this table for the list 2, but in the list 2 there is only one pair, 2 and 3. So let's consider the corresponding route to check, and demand here is the following. So for the customer 2, demand is 35. For the customer 3, demand is 30. And we see that the total demand is 65 units. And we see that in this case, this route is feasible because 65 is less than 100, and so the current route is 0230. So, and there is nothing to add now, so, and that's it, and this is the route number 2. So, and let us consider the ranked list, and now when the second route is found, it is 0230. So we exclude this pair from the list, and there is no list 3. So we should stop here. All the customers are satisfied. And now let us calculate the corresponding distances. So the distances. So we consider the first route 01540. So we see that the distance between the central warehouse and the first customer, according to the problem statement, so we can go to the problem statement and see the distance between 0 point, so central warehouse, and the first customer is 28 kilometers. And the distance between first and the fifth customer is 20 kilometers. And the distance between customer 5 and 4 is 25. Between 4 and 0 is 25 kilometers. So it means that the distance for the first route is 28 plus 20 plus 25 plus 25. And the distance is 98 kilometers. And it was the first route, and let's consider the second one. So it is 0230, and here the distance is 31 kilometer for the central warehouse and the second point. From the second and third point, so the distance is 38 kilometers, and from the customer 3 to the central warehouse, so the distance is 20, and we summarize all these distances, and we will get 31 plus 38 plus 20, and it is 89 kilometers. So, and if we summarize distance of the first and for the second route, so we will get only 187 kilometers in total. So it is the total distance for both routes, and also we may calculate the corresponding demand which we satisfy. So demand of the first, fifth and fourth customer for the route 1, so it is 94 units, and for the second route, so demand is 65 units. Of course, the total demand which we satisfy according to any solution, if we visit all the customers, so of course the sum of the satisfied demand will be the same every time, but the total distance could vary if we consider different solutions. And so according to the sequential saving algorithm, we found two routes, and first route distance is 98 kilometers. For the second route, the distance is 89 kilometers. The total distance according to sequential saving algorithm is 187. So you may also continue with the paper, and you may continue with the parallel saving algorithm, and you may also find a solution and compare the result with the sequential algorithm result. For the parallel saving algorithm, the total distance will be different, so it will be not the same 187. And in general case, we cannot say that which algorithm is better, sequential or parallel one. So sometimes one is better, sometimes another is better. So, and if it is really important to find a better solution, both these algorithms that do not guarantee optimality, but if it is possible, so we may calculate both this algorithm to find the solutions according to these both algorithms, and just choose a solution which brings the smaller distance. That's it. Thank you for attention.